All right. So, hello and welcome everyone to the fifth week of interactive live sessions for the course on computational fluid dynamics for incompressible flows. This course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras, and I'm the TA for this course. And like every other week, we shall be solving some problems together and discussing doubts, thoughts, and anything and everything related to the course. So before we begin, let's start with, if you have any doubts or questions from the previous weeks, maybe this would be a good time to ask them. So the floor is yours.
Hello.
Yeah, hello.
Yeah. So actually, my first question is about this sparse matrix. Like
Oh,
diagonal
mm,
matrix also have a lots of zeros in it.
mm.
So a diagonal matrix is also a sparse matrix.
Yeah, obviously.
Okay. So
It's
then,
in fact
what is
one
the
of the
benefit?
Yeah, it's a diagonal matrix is in fact one of these sparsest matrices you can think of because it's only the diagonal elements
Okay,
which
but
matter. Yeah. Yes.
okay,
Yeah.
so it was
Mm,
told that taking the
mm,
inverse of an sparse matrix
mm,
will take lots of computational data and storage, and it is difficult to take the inverse. That's why we go for iterative methods like Jacobi and all that.
mhm, mhm,
But in Jacobi, we assume that A approximate
mm,
for the correction vector phi
mm,
dash. For
mhm.
that, we assume it to be a diagonal matrix. So we begin with the idea then that sparse matrix is difficult to take the inverse, and we end
Mm.
up taking approximate matrix as a sparse matrix.
Yeah.
So
So
that's
there
what
are
my doubt is.
Okay, so there are two things. First thing is it's not that sparse matrices are especially difficult to take an inverse of. Any matrix, once it becomes big enough, getting an inverse of that is difficult. Now, sparse matrices, I think it's a little bit easier, but then again, the whole business of finding out inverses of large matrices is not a good idea. And the second thing is about the the correction term being assumed as a diagonal matrix. It's because the original one was a diagonal matrix as well. So there's a high chance that the uh, inverse of it will also be diagonal. So that is a reasonable assumption to make over there. Does that make sense?
No, a little okay. That's I
Mhm.
understand that. Okay, one
Mhm.
factor I understand that invert taking inverse is difficult. That
Mhm.
is okay,
Mhm.
but it was specifically told
So can you
in the video
mention which
that
lecture so then I
sparse
can
metrics are
go back and.
in the very beginning, like in the like when in the elliptic equation when they were introduced.
Okay. Okay, so sparse matrices, I'll take a look at that. Okay, so your main question is, if I understand, is that why are we going about finding the inverse of a sparse matrix even though we are telling that it's difficult, right?
Yeah,
Okay.
we're not taking inverse, but we
Hmm.
assume the in the Jacobi the approximate A matrix as sparse
Hmm.
matrix because it is a diagonal matrix. We assume it to be diagonal.
Mm-hmm. Yeah, that's the thing. So,
Yeah.
from previous knowledge, we know that the form of this matrix will be a diagonal one. So that assumption is a reasonable one to make. And then we go ahead and try to find out the values of those diagonals. So it's a priori
Okay,
knowledge that
and
it
what?
may be that way, which helps us do the calculation. Yes.
Hmm.
Sorry. Go ahead, please.
But at the very first place, how
Hmm.
can you have some idea like why in Jacobi method we come up with the idea of taking the approximate matrix as diagonal matrix? Like yeah, randomly, why we just come up with that idea? Like there must be some
Hmm.
logic behind it.
Yeah, it's not totally random. So if I remember correctly, so what we, yeah. So what we do in Jacobi method is that we have some matrix A which works on phi and gives us another vector B maybe something similar to that, right? So both phi and B are uh, vectors that is only column matrices. So mm, yeah. So here, if we know that if we now do this, so some inverse of this matrix into another vector. So so this is a vector and this is another matrix. So imagine this. So I assume that it's a diagonal matrix, something similar to this. So there are some values in the diagonals and zeros everywhere. And I have one vector over here. So these are the values of it. And I know that this should ultimately give me another vector as well, because that's what the form of this thing is. Right. Well, that does not prove that it has to be diagonal, but okay. Anyway, I'll go back to this and I'll come back to you next session with a more concrete answer. Okay.
Yeah, actually, I get this where it is in the it is in fourth week, second lecture,
Fourth
where
week, second
iterative
lecture.
methods are introduced.
Okay.
Yeah, there it was told that phi is equals to some phi guess value, phi g
Mm.
plus phi dash, which is an approximate correction, right?
Okay.
After
Okay.
that, we make a little computation,
Mm.
like taking, then we come up with that a approximate, and there
Okay.
we we go ahead and take it as a as not in folds. Okay, then
So,
we take, go ahead and taking it as yeah,
okay. So let me
taking it
try
as
to
that.
yeah. So let me try to find out the
Okay, go ahead.
lecture notes, so that way it may be easier, right? So you can see my screen, right?
Yeah,
Okay. So we have iterative methods, and let's take a look
not
at
in
lecture notes.
two, it's three. No, linear solver, right?
Linear solver.
M fourth weeks and fourth lecture, I
Yeah.
guess.
This is the one, right?
Yeah, yeah.
So we have over
Yeah, four.
here.
Yes,
Yeah,
this
so this
one.
is what you're talking about.
So
Yeah.
here,
Hmm.
yes. In the very next slide, please
Hmm.
come to the next slide. Yeah, this one. Now
Hmm.
this A approximate,
Hmm.
which is getting multiplied
Hmm.
with phi dash, we
Hmm.
take this A approximate as D,
Hmm.
right?
Yeah.
And one thing is like we how we come up with that idea of taking this as D, and in the very next point go as settle, we come up with the idea taking it as L plus D. Now, what is the
Okay.
logic behind that?
Okay. Okay. I understand your question. So this will, depend on the original formulation of what the Jacobi method is. Yeah. So over here in
Yeah,
Gauss-Seidel
here we take
method,
it
we
as a
take
L plus D.
L plus D. Yeah. Yeah.
Yeah.
Got it.
So, what is the logic behind it?
Hmm.
Like,
Hmm.
it is going to
Yeah.
give
So
us.
let's go back to what the Jacobi method did. It should be here. Yeah, so this is what the Jacobi method does for a 2D heat diffusion or some kind of diffusion problem, right? So In the Jacobi method, we do not use the older values. We do not use newer values. We only use the older values of the neighboring points, which is I plus 1, comma j, I j plus 1, I j minus 1, I minus 1 j, and all that. So these 4 points at the earlier iteration, that is at the kth iteration. And that's what gives me k plus 1. So if I write down this whole thing in a matrix form, these equations. So I'll have, you know, uh, one matrix containing these coefficients, which are similar to a beta square over 2, 1 plus beta square, those things. And I'll have, four different values of these um, neighboring points. And on the other side, I'll have this value that I'm explicitly calculating, the one at k plus 1th point. So that's why the matrix being multiplied to k plus 1, that's a diagonal matrix because that has only 1 as coefficient. Whereas in the Gauss-Seidel method, I have a mixture of newer points as well as older points. So in that matrix, for wherever you're multiplying with
No,
phi
no.
k plus 1,
Actually, this. Just a minute.
yeah.
This we come up while first we assume that A is a diagonal matrix. Then we solve it and we come up with this idea. Like in the previous slide,
Hmm.
we have assumed, and then while after solving, we come to this idea, this formula. Not this formula is not giving us that A approximate is diagonal matrix.
Yeah,
Is
no, yeah,
first
that's
we assume
no,
that.
that is the direction that it goes. We start from here. We know that this is what the Jacobi iteration method is, or this is what the Gauss-Seidel method is, and that's what tells me whether the matrix is being multiplied to phi k plus 1, whether it's diagonal or lower plus diagonal.
Sir, I have also
Okay,
done
can
the
you?
same method that Boogie did. The superscript, we are sometimes so we are writing k plus one and also we are writing k. So could you explain when we have to write the k plus one and k in the superscript?
Shubhangshu, your voice is breaking up. It wasn't clear what you tried to say.
Sir, when we have to write k plus one and k in the superscript.
Hmm. Yeah, so the k plus ones are the unknowns and k's are the knowns, which are from the previous time step. So let me just try to do this. So these are, okay.
Wait a minute. Can you please go to the previous slide? Then I can explain.
Yeah,
The
sure.
very first slide, please. A little bit more.
And this one,
Yes.
lecture 2 or lecture 4? Which one?
No, no. Lecture four.
Lecture 4.
This you come in elective. Not this is the elective in
Yeah,
fourth lecture.
I'll go to the fourth
I
one.
guess
Yeah.
linear solver.
Mm. Yeah.
Yeah. Here.
Yeah.
Yes.
Mm.
Okay. So here it was now in the next slide we assume that it is going to be the. Yeah, here
Mm.
we have assumed that D is
Yeah, so the
A
form of
approximate is
the
equals to
A
D.
approximate is D. Yeah. And we get to know that from the idea that we know what the Jacobi method does. We know that in the Jacobi method we have, 1 being multiplied to phi k plus 1 and some other coefficients being multiplied to all the other values of phi which are at the kth
Oh,
iteration. So this is where we get the clue that
I'm getting some.
whether that
Yeah, yeah,
matrix
yeah.
will be
Maybe.
yeah.
Yeah, now I understand what you're trying to. Okay, okay, okay. So
So
I will
this
see into it. Then
yeah,
I will.
okay, so we
Yeah,
have
because right
this
now it is
knowledge.
difficult to imagine.
Yeah, I
Yeah,
understand
yeah,
that,
yeah.
but yeah, so this knowledge, we start with this knowledge that gives us a clue that the those matrices can be only diagonal matrices or lower plus diagonal. That's right. Hope
Okay,
that
okay,
makes
okay.
sense, right?
And
Yeah.
yeah, that is okay. But only
Hmm.
doubt is also one thing is like we might have assumed as a diagonal matrix, which is a sparse matrix. but at the same time we are not taking inverse while solving it,
Hmm.
so that is also okay.
Yeah.
Yeah. Okay. So
So
these two
that
doubts are clear now. One,
Hmm.
yeah, please go ahead.
Hmm. So that prior knowledge helps us to make those guesses and do a easier calculation than what we would have done otherwise.
Okay. Now one thing is like in
Yeah.
we have in one of the example, I don't remember the lecture,
Hmm.
but there is some doubt.
Yeah, so Shubhanshu, can you hold on for a minute? Let's finish up with him, then obviously we will get back to you. Sorry about that. Please, have some patience.
No,
Sorry. Yeah, so Shivang, let's finish up with your doubts. What else do you have?
no, I have multiple doubts, so I had asked
Hmm.
one, then give other chance.
Sure.
Okay, so one
Okay.
is like at one place,
Hmm.
it was told that some equations are governing equations are discussed, and it was told that if we have like a fluid, a stationary fluid,
Hmm.
and we put a plate in between,
Hmm.
and we suddenly push that
So,
plate with a
yeah.
velocity u in particular direction, then
Yeah.
it is a kind of maybe parabolized Navier-Stokes equation. Maybe, I'm not
Yeah.
sure. So, but the problem is, like in that particular case, it was told that if the plate is assumed to be infinitely long,
Hmm.
then the
Hmm.
pressure gradient can be neglected.
Yeah.
It is zero.
Yeah.
Like how pressure gradient can be zero?
Okay. So imagine you have an infinite plate like this, which is, infinite in this direction as well as in this direction, right? So this whole infinite idea tells us that at any point that you take in x, so this is x direction. So at any point that you take, it's symmetric. So whatever is on the left of that point, the same thing is there on the right side of that point. So any variable you take, it's symmetric about that point or that line at a particular value of x. So that's what the meaning of this infinity is.
So
Now, what that does is that
no, no.
uh, yeah.
Yeah, yeah. Go ahead.
Yeah, so what that does is that it diminishes the uh, reason for having a pressure gradient in this direction because you can have P1 here, P2 here, P3 here, P4 here, and if you're going to infinity, that means it will go to zero at some point in this direction and infinity in this direction. So these are, although these are independent things, but these are sort of tied to each other. So in this case, you don't
Sorry, I
need pressure
don't
gradients.
understand.
So, yeah. So, I'll give you a
No,
simpler answer. So forget about this symmetry. So the thing is, there is no pressure gradient which is driving the flow. It's only what is called a momentum driven flow, meaning it's the wall that is driving the flow. That's similar to what we learn in Kuwait flow as well, right? So we can have no pressure gradient, but if one of the walls is moving, then we have a flow due to that. So this is also a similar case where it's due to the motion of the wall that we have a flow in the fluid surrounding it,
okay, but okay, okay.
and not
Yeah,
necessarily
but
due to pressure gradient.
yeah, yeah, that's fine. But
Hmm.
why would we need that infinite
Yeah, we need that.
assumption that
Yeah,
let keeps
the infinite thing we need for two reasons. One is this symmetry idea that I talked about. So any point you take, you have symmetry about it. So basically, dodo x of anything vanishes. Okay, so that's what
why?
allows us to. Yeah, because so what does the symmetry condition does? So you have a symmetry boundary condition. Maybe if I take a axis symmetric geometry, for example, a cylinder like this. So at the axis, what do you have? And let's call this direction coordinate r. So at this axis, at r equal to zero, what happens? All derivatives of r become zero, right? Because it can't change over there. Something like this. So you read up on symmetry boundary condition. That will give you an idea.
చిన్న క్యాలిక్యులేషన్ చేయమను చిన్న చిన్న క్యాలిక్యులేషన్ మల్టిపుల్స్
Okay.
అడిషన్ సప్రెస్ ఉంటాయి కదా అయ్యేది
And
అడవాంటేజ్
another thing is in this
నేను కూడా టైం
plate
వేస్ట్ అయినా
case, if we had a finite if we
చిన్న
had a
క్యాలిక్యులేషన్ కూడా
finite
చేస్తాను
plate like this, then wall effects would come into the picture. So we want to avoid that as well. We want to keep it simple, the mathematical formulation simple, which is why the geometry is assumed to be infinite in the x direction. Okay.
Okay, this wall effect is I understood, but
Hmm.
still this del by del R thing is
Yeah.
difficult
So
to
you
understand
read
because
up.
we can
Hmm.
yeah, we can have pressure gradient like this because in this direction. What's the problem in that? Like we could
Problem
have
is that,
possibly
yeah, so let's say this is what P versus X is, right? So this is P in this direction and X in this direction. So if you have an infinite direction, then pressure would reach zero and go negative at some point, and at the other point, it will approach towards infinity. You get the
okay. I
point,
will
right?
see into it. Okay,
Yeah.
you can go with other doubts, then I will ask.
Okay. Okay. Thank you so much. Yeah, let's go back to other people. Shubhangshu, what did you have? I think you wrote something in the chat box. Sir, please explain when we write phi n plus 1 in superscript and n in superscript. Example, in line succession over relaxation method. I have confusion in this. I have posted my doubt, but got no reply. Okay, sorry about that. But yeah, so superscript n plus 1 and n simply mean what time step you're worried about. So basically, um, we move in time. So let's take an example where we have time and space as the two variables. We have, let's say, x in this direction and t in this direction. So at a certain t, let's say at t equal to 1 second, I have this thing where my um, time step number is n, and the next one, let's say at t equal to 2 second, where the time step that I'm taking, delta t is 1 second each. So this next one will be n plus 1. And the corresponding phi over here, they will have superscripts corresponding to that. So over here I'll have Pn plus 1, over here I'll have Pn, and which one we use where depends on the formulation. So in case of backward time central space, forward time backward space, whatever formulation we're using for discretizing, that will dictate which one do we use.
Sir, sir,
Yeah.
for example, in
Hmm.
point Gauss serial iteration method,
Hmm.
uh, if we look means if we look the x and y axis, so
Hmm.
in towards positive x, we write I plus one comma
Yeah.
j,
Yeah.
and in middle we write I comma j.
Yeah.
So for phi I plus one comma j, we have to write k plus one.
Hmm.
So for in this same question,
Hmm.
for phi I minus one comma
Hmm.
j,
Hmm.
we have also written k plus one. So
Ah,
I think that we have to write the k, either we have to write the k or something k minus one here.
yeah, so I think you're, mixing up two things over here. Sorry.
So
Yeah, yeah.
it's
So,
the in the uh, can you please open the lecture PDF
hmm,
week
yeah,
4 lecture 2.
week four, lecture two. Okay, that should be easy. We were looking at, yeah, I have week four, lecture two over here. Tell me. This is slide one, slide two.
Yes, sir, in this same point
Hmm,
Gauss Seidel iteration
hmm,
method.
yeah.
So
So,
in this,
hmm,
yes, sir, please explain it once again when we have to write
okay.
k plus 1 and k.
Yeah, so basically, whatever value is known to us in point Gauss Seidel method, we use that. So when we are going from, we start from I equal to 0 and we go to I equal to whatever the maximum value of I is. Let's call it capital N or something like that. So while we are calculating the values of phi I comma j, so let's take for example I equal to 5. Okay.
Yes, yes.
So when we are calculating this, that means we have already calculated the phi for I equal to 1, 2, 3, and 4. Then only we are calculating 5. So while we are doing
Yes.
that, so that is why for phi I minus 1, I take the value at k plus 1 because I have already the new value of that one because I have already calculated it before.
Okay.
Similarly, J also we start from J equal to 1, 2, 3, 4, and then go. So if J is let's say 6 and over here J minus 1 is 5, that means I have already calculated this value earlier. So for this one also I'm using K plus 1 because I have the newest value or the K plus 1th iteration value of this variable. But for the next ones, that is for I equal to 6 and j equal to 7, then I don't know. So those values, that is I plus 1j, then I comma j plus 1, for those I have to use the older values, which are k, at the kth level.
Okay.
Okay.
These values are unknown, so we these are unknown, so these are previous iterative.
Hmm. Yeah, so earlier we knew what the value was. That's the one that we're using. And for those variables that we already calculated this time, we can use the newer values.
Okay, so
Okay. And here k plus 1 are not time steps. These are just iteration steps because there is no time in elliptic problems, right? So it's just iterating over to find the value at the the final solution, the steady state solution, whatever. Okay. Anything else? Okay.
sir, I have posted one question,
Yeah,
sir.
yeah,
I
yeah,
try
yeah.
to solve it in this question.
Yeah, I'm looking at it. So a long thin rod with a length of 10 centimeter has a fixed temperature of 100 degrees C at the left end and 50 degrees C at the right end. The initial temperature of the rod is 0, okay, with diffusion coefficient something. Using forward time central space with delta x and delta t given, the temperature at distance
Uh,
of 2 centimeter from the left end after zero
Excuse
point
me.
0.2 second is, yeah,
Yeah, actually, please don't go for this question because I had question about this thing. Then please solve this question because it is related to the same thing which what I'm going to ask. If you can do that, please.
yeah, please go ahead and ask your question then.
Yeah, then it is related actually
Hmm.
about from the same thing. So
Hmm.
can you please open the lecture number week 5 lecture first? This same
Lecture
thing,
number?
forward time central space. Week 5 lecture 1.
Okay, okay. Yeah, can you see the screen?
Yeah, yes, this is
Hmm.
the, yeah, this is the parabolic. Okay. Yes, so in this this same thing, forward time and central space method.
Hmm.
Next
Hmm.
slide, maybe. Next slide. Further next. Yeah, this is just wait a minute.
Hmm.
Yeah, this previous slide. Previous. Yeah, here, just here.
Hmm. Hmm.
Okay, in this in this method, forward time and central space, what I assume that we are moving forward in time and we are using central spacing in space, right? That was mean.
Yeah.
Okay,
Yeah.
yeah. So now
Yeah.
when in lower it was written forward time del phi by del t is equals to phi I n plus 1 minus phi I n.
Hmm.
So here if I am using forward differencing,
Hmm.
then I must go ahead in time, and the present time is n plus 1. So I must go for n plus 2 actually.
No, no, no.
Because in
So
forward time,
let's
what?
so forget about time. If you want to take forward in space for dou phi dou x, what will be the formula for that in the discrete version? Forget time for a second.
There
Let's say,
also we
uh,
go I plus 1 minus I. We go
yeah,
for right.
yeah. So that's exactly what we are doing here. N plus one minus n.
No, but here n plus 1 is assumed to be the current time level. N plus
Yeah,
1 is
that's
said to be
the
the current time
unknown.
level,
Yeah,
and n is the
the
previous.
yeah the unknown one is n plus one, and the all the known ones are n.
What?
So you're trying to find out what the value of phi I at n plus 1 would be. That's the unknown that you're solving for. All the values at n are already
Yeah.
known. Those are from the previous time step. So
Okay.
you see this
But
template over here on the
like
right end. Can you see my cursor? So n plus 1 is the present or
yeah.
current time level, and n is the previous time level, which is already known.
Okay. Can you make one line over there and simply in
Line
Excel
over there as
simple
in.
a line and I plus 1 I minus 1. Can you draw?
We already have this one, right? So what do you want on top of? Do you want something on top of this
No,
figure?
no, no. Yeah,
So
it is going to
okay,
be difficult then.
I'll make a
You
new
need to.
figure. Hold on.
Yeah. On
So
the same
let's
slide, if you make, then it will.
uh, those are PDFs, so I don't think I'll be able to edit them. I can try
Okay.
that, but
So
let's
make
see.
it
Let's
there.
give it a shot. So I am drawing a line here. Tell me what you want. So I have phi I n.
Uh, I don't
Okay.
write phi. Simple
Yeah.
I plus 1.
Okay. I plus one, I minus one.
Okay. Now, if for this, if I write a forward difference method at
Hmm.
I
Hmm.
for any variable,
Hmm.
what I will write
So let's say I want to
is,
find out
let's say
dou
del
phi
phi
dou
by del
x
x is equals to
at I.
phi I
Yeah.
plus, yes.
Yeah. So what
Then
will
I
you
will
write?
write
Hmm.
phi I plus 1,
Yeah.
phi I plus 1 minus phi I divided by delta x.
Yeah.
Right. So it is forward because I move ahead of the present time, of the
Yeah.
present space.
Yeah.
I move ahead.
Hmm.
And then okay, now if I go for time step, now you
Hmm.
can make a vertical line.
Hmm.
So please make a vertical line and draw the same thing vertical. Yeah, now this is time and out there.
So now let's say you want to find
Yeah,
what dou phi dou t is at n.
now I am at n.
Hmm.
Then I go for n plus 1 minus n
Hmm.
by delta t.
Delta t. Sorry.
Delta
Yeah.
t.
Hmm.
Yeah, but in this case, n
Hmm.
is the level where I am.
Yeah.
Now in the
And in this
in
case,
that
I was the
it
level
was
that I
shown
was
that
there.
n, yeah, and in this case n is the level where I am.
Hmm.
But there in that method where forward time and central space, n
Hmm.
plus 1 is the level where I am at present. That is
See
my doubt
over
because n plus 1,
over here
I
also.
am at n
Yeah.
plus 1.
Hmm. Yeah. So what's your problem
I'm
over
not
here?
at n. I'm not. I'm at. Yeah. I think you understand what I'm trying to say.
Here we are trying to find out what dou phi dou t at n is, and that gives us this. Here we are trying to find out what dou phi
Yeah.
dou x at I is, and that gives us this. These are exactly analogous. You can see the symmetry between these two, right?
Yeah.
And so over here, it was the n plus 1, which was unknown, and every value at n is known, and we are using it to calculate the value at n plus 1. Similarly, over here also, it's the value at I plus 1, which is usually unknown, and all the values at I and earlier are known. So we go from I equal to 0 to 1, 2, 3, so on. Similarly, n also we start at some initial 0 or 1 and we keep going ahead. So we have some
Yeah,
known
but in
values, we keep
parabolic, what?
marching forward. Hmm. Tell me,
Yeah,
parabolic, what?
that's fine. But
Yeah.
in that case,
Hmm.
in parabolic, we are at n plus 1 level. That's what my doubt is. If we are
Hmm.
at presently n plus 1 level, then I don't
Hmm.
think why should I go if I and I am merging in time, then I will go
Hmm.
for next. That is my
You'll
doubt
go
is.
at n plus
I
2,
will
is
go
it?
for next. Yeah, that is what I'm saying. If I am standing at n plus 1, I will
And
go n plus 2.
see, this n plus 1, n plus 2 doesn't really matter. What matters is what you know and what you don't know. So basically, you start with some initial condition at t equal to 0. You don't know what the value at t equal to 1 is. So that's when you go to t equal to
Correct.
1. T equal to 1 becomes your current value. And then you
No,
use
no,
the
that
values known
just
at
a
t
minute,
equal
just a
to
minute.
0. Okay.
No, no. So if I am using some value which is known at previous time, then why it is forward time? Then it will be a backward time method because we are using previous values.
No, no,
I'm not.
backward in. Okay, I'll tell you what backward is, then
Okay,
maybe this
then
doubt will get cleared. So,
no, no.
backward
Yeah,
in
yeah.
time
That is
is,
what I'm saying. Please
yeah,
open lecture. No, lecture 5, lecture second of week 5. There it is a backward method. Next lecture of this.
yeah. So, Larsson method is the one. Yeah.
Yeah, here also like we use same thing n plus 1
Hmm.
divided by n,
Hmm.
n plus 1 minus n
Hmm.
in pi I. Here also
Yeah.
that's why I got this doubt.
But in the right hand
Here
side, you
it
can
is
see, right?
okay. Like
You're using all the unknowns at n plus one, and then trying to solve for this whole
right
thing.
hand
And
side is completely different.
yeah.
No, no, right hand side is completely different. It is about space. Space I
Hmm.
understand how it is drive. Yeah, what I'm worried about is here also in backward time is we are using same formula and
Hmm.
here it is valid. Yes, we are using previous knowledge and we are moving ahead.
Yeah.
But
But
there also we are using
yeah.
previous knowledge and standing at present time.
So how much previous knowledge and how much current knowledge you are combining, the ratio of that actually is different between the backward time and forward time method. So the spatial derivative, the dou2 phi dou x2 in the backward time method, in that case, that spatial derivative is taken for the current time step, the unknown values, the ones at n plus 1. And in the time marching process, which is the forward time central space method, over there you take all the known values of phi for calculating the central in space thing. So over here you will have all the counterparts at phi I plus 1 n, phi I n, then phi I minus 1 n, those values, numbers that you already know. Over here in the backward time process, you don't know these values. You're just creating a formula, and then after that, you try to solve for all of those variables simultaneously.
No, I don't understand because the problem is like here also we have used n plus 1 level,
Hmm.
like present level we are using. So if we are using central spacing
Hmm.
and we are at n plus 1 level,
Hmm.
right? But
Yeah.
in the forward,
Hmm.
forward I guess we have used nth level
Yeah.
for central space. Like that is the another doubt. Actually, first
So let
thing,
me
first
try
doubt
to,
is
yeah.
that
So
at time level why we are,
let's clear
yeah,
this one first,
I
then
should
move on to the other one.
yeah, don't go for the space thing, otherwise it
Hmm.
will confuse. That is another doubt because in forward we take nth level and in
Hmm.
backward we take n plus 1th level in space.
Hmm.
And in first doubt is about the time step.
Hmm.
Like in
What is
forward
it?
we have how and backward we are using same formula. In
Hmm.
time step we are using same formula. In while discretizing
Yeah.
time, we are using same formula for backward and forward.
Yeah. So let's do away with n and n plus 1 and n plus 2, all that for now. Let's try to write in terms of known and unknown. Known is earlier values which we have calculated, and unknown are the ones that we do not know yet. Okay. So let's use a different notation over
Yeah,
here.
yeah, yeah.
So
Okay.
I'll call this phi u, u meaning unknown, and phi plus 1 u, phi minus 1
Hmm.
u, and known ones I'm calling them k. Okay. So phi k, sorry. So phi k, phi plus 1 k, phi minus 1 k. These are all known values like 2, 3, 4 numbers that we already know. And unknown values are these are unknown variables. We do not know what their values are. So what we do in forward time central space is that we just calculate one unknown at a time. So we calculate phi k minus phi, sorry, only one unknown. And we use pi k over here, some delta t, and over here we have all known values. So k I minus 1 minus 2 phi I k plus phi I plus 1k. So these are all known numbers 2, 3, 4, 5, like that. And we find out what this one unknown is. That's all. That's what the forward time method does. And what you do in backward time method is that you use the same thing. So you have one unknown over here, and the right hand side also you write in terms of unknowns only. So you write phi I minus 1 unknown minus 2 phi I unknown plus phi I plus 1 unknown divided by delta x square. And then you try to, this is the only known value over here. These are all unknowns. Then you put them all in a matrix and you simultaneously
Hmm.
solve for all the unknown values. This is the difference between the two methods. Does it make sense?
Very much.
Okay.
Actually, uh, but but the problem is why the name is this and forward time, and this I'm confused.
Okay,
Because
so
if I go by
okay,
this known and unknown,
okay,
then I understand.
I'll tell that as well. So it depends on the perspective from the known case. So if you're s- so in this case, forward in time, you're using the known values in the right hand side, right? So you're standing at the known level and looking at the unknown one and trying to find that out. So that's why you're looking at the forward time. And for the backward time, you're already standing
Okay.
at the
And
unknown.
backward.
You're already standing in the unknown in case of backward time, and then using a few values from the known values from the backward
Oh,
time. That's why it is backward time. Does
Sir,
the
can you
term?
please continue
okay,
my
okay.
question?
Yeah, obviously. So we got stopped over here. So let's get back to your thing. So I have a long rod like this, and everything starts at 0, and we have 100 degrees Celsius at one end and 50 degrees Celsius at the other end. These are Dirichlet boundary conditions, and we have a known diffusion coefficient as well. I'm not worrying about the number for now. And there are given delta x's and delta t's as well. So in your case, you just have to calculate. I think this is just a calculation exercise. So basically, and your initial condition. So all the t at the all the temperature at time t equal to 0 is basically 0 degrees Celsius, right? And you have to use forward time central space. So things that we already spent some time on over here. So basically, you have uh, phi n plus 1 equal to some function of known values, right? Phi minus 1 k, phi not k, sorry, at n, n, and so on. So It's asking us what the temperature at distance 2 centimeter is, and from the left end after zero point 0.2 seconds. So I think you have to do a lot of calculations if you're doing it by hand. It's better to like write a code and find this out.
Sir, I have used the heat conduction,
Hmm.
steady heat conduction equation,
Not steady,
del
unsteady. Yeah,
unsteady, yes,
yeah.
unsteady.
Hmm. So the your
Uh,
equation would be this one. Dou dou
yes,
t.
sir. Del t
Hmm.
by del
Hmm.
t
Hmm.
del t del square t by del x square. Yes,
Yeah.
sir, I am using this.
Hmm.
And sir, I have also made the formula, but I am getting confused. Means if I write the phi in terms of temperature,
Hmm.
so means मतलब मुझे कौन सा टेम्परेचर की कब वैल्यू रखना है, मतलब कौन सा मैं
Hmm.
इनिशियल मानूं, कौन सा मैं 100 मानूं, फिक्स्ड मानूं, उसमें
Hmm. Hmm.
कौन
Hmm.
सा मुझे वो, तो उसमें कंफ्यूजन हो रहा है मुझे बहुत।
Okay, okay. So basically, these things are also given, right? So this is x equal to, sorry, x equal to 0 centimeter. Then you have x equal to L, which is what, 10 centimeter. Then your delta x is 2 centimeter. That is one good thing. So basically, you have to find out this number x1 at you know um, two time steps later. So t equal to zero point 0.2 second. But this whole thing has to be solved. Like there will be 3 4 points over here. So everything has to be solved. So basically,
Sir,
you break this down.
can
Yeah.
you do for can you do for x equal to 0, sorry, for x equal to 2 centimeter,
Hmm.
so that
Yeah.
I will proceed.
Yeah. Yeah. So I'll do that. So initially, all your x values are zeros. So you have five values, right? At zero,
సప్లై అయిపోయినాయి మొత్తం మీద
0 centimeter, 2 centimeter,
అలా
4 centimeter,
ఇప్పుడు 7
six, eight,
పది నిమిషాలు
10.
రేపు టెంపుల్కి వెళ్తున్నాం
So
మంగళవారం
1, 2, 3, 4, 5, 6.
టెంపుల్కి వెళ్తాం
Can you please mute yourself, whoever is on unmute, if you're not.
ఇల్లు ఈ టైంలో వస్తారు
Uh, um,
7 ఉండొచ్చు 8 ఉండొచ్చు 9 కూడా ఉండొచ్చు
Tirupati Reddy,
కదా
you're on unmute. Can you please mute yourself? Yeah, thank you. So basically, we have six values of x, and all of them will evolve in time. So t for all of them. So there will be six values initially, right? T1, I'll call it like at small t equal to 0 second, which is when we are starting the problem. So then it will be six zeros basically, because I've been told that the initial condition is all zeros. Then in the next time step, when t equal to what, zero point 0.1 second, then I'll calculate the value of temperature there using our time marching formula, which is Tn plus 1 I minus Tin by delta T equal to, um, over here we'll have alpha, then delta x squared, Tn I minus 1 minus 2 Tn I plus Ti plus 1 n. So using this whole formula, I'll get some formula of Tn plus 1 using all the earlier known values of Tn, right?
Yes, sir.
You get this
So,
step,
sir,
right? So that
for
will
Ti
give.
minus 1, what we
Hmm.
have to take, and for Tn I minus 1, what value we have to take? So, can आप थोड़ा
Uh,
गाइड कर दीजिए.
which one? Sorry. Uh,
Sir, for Tni and for Tni minus 1
hmm.
means
Hmm.
what value of
Hmm. Hmm.
temperature we have to take,
Hmm. Hmm. Hmm.
50 degree or 100 degrees. So please
Yeah,
explain this.
yeah. So basically, यहाँ पे these won't be all zeros. So at the boundary, so I know at 0 centimeter, t is 50, and at t equal to and x equal to 10 centimeter, t is 100, and that will remain the same throughout. So later on also it will be 50 here and 100 over here. In between these 4 points, They will change every time. Every time you calculate, these will change. Then at the next time step, t equal to 2.2 second also, you find out what the values are. So it will be again 50 over here and 100 in the end. Those are the boundary values. And in between, again, you have to calculate these numbers based on this formula. Where,
So I'm not
yeah,
getting. So can you please solve by putting substituting the values in the formula?
okay. So okay, so first step I have this thing 50 0 0 0, then 50 4 zeros, then 100. So if I'm trying to calculate T2, um, okay, so let's use superscripts here. So those are times. So I'll call them T1, T2, T3. I'm trying to calculate this one, okay? तो इसे मैं बोलूँगा T2 2. So I value 2, N value also 2. So for this one, I'll have alpha delta t divided by delta x square. These are all known things, by the way. You know the numbers. And over here, I'll have ti minus 1 n, which is 50, then minus 2 into 0, then plus 0. And I'll add tin, which is again 0. So if I So can you quickly calculate this one? Alpha, delta t, and delta divided by delta x squared?
So it is coming 0.02.
0.02. Okay. Into 50. 0.1
Okay.
or 1, is it?
So in place
Into,
of ti minus 1, you have put it 50. And in
yeah,
place of t and I, you have taken 0.
yes. So,
Okay.
so while I'm trying to calculate this one, I need these three values. This is I minus 1, this is I plus 1. These are
Okay,
giving me
sir.
this one.
Means these between these four values
Hmm.
means 0, and for uh, T2
Hmm.
means then after 0 the 1, then we have to put the 1. You might minus
Yeah.
50
Y- Yeah.
minus 2 into 1.
Yeah.
So it not 1, 2. It's 2 centimeter because
Hmm.
interval is 2 centimeter.
Mm-hmm. Delta x is 2 centimeter. Yeah. So basically, this gives you this number. This is something like 1, if you're correct. So this gives me 1 over here. Now, these three things are 0. So I imagine this one will also be 0. These three are 0. So this one will also be 0. And this one, again, some number will be there because I have 100 going in here. So some number over here. Then in the next step also you use these three numbers, 50, 1, and 0. You put them in place of I minus 1, I, and I plus 1. And then that should give you this number. This is the number that you have to finally calculate.
Okay, sir.
Does that help?
Now I got it. Yes, sir.
Okay, cool. It
Sir,
seems everyone else has left.
sir,
But
I
okay.
have one issue, sir. I am
Yeah.
posting my doubts
Hmm.
on a discussion forum,
Hmm.
but I didn't get reply from the instructor over there.
Okay, okay. It's usually the TAs who look into it. I'll also try to inform them. Okay.
Okay, sir.
Mm, cool.
Thank you, sir.
Okay, no problem. So let's get started with my questions. So we have question
Just a
number.
minute.
Yeah, okay.
Uh, I
Please go ahead.
actually I have
Mm.
yeah. Can you open that where you're writing those? Just that slide. Yeah, not that. You have just explained that method, right?
This one?
Yeah, here.
Mm.
So yes, and my question is here like I usually try to see this forward time and backward time in the same manner as we discretize the space.
mm,
Like if I am standing in a space, then I must
mm,
look forward
mm,
and like
mm,
that. But
mm,
here you have explained a really different thing. Like forward time means this thing, like in the terms of known and unknown. Like if I am standing at known
mm,
and looking forward, then it
mm,
is forward time.
mm.
So the so always this formula gets changed. Like uh, my question, let me formulate in a much better
Mm,
way.
mm,
The forward and backward differencing
mm.
in time
Mm.
is different than forward and backward differencing in space.
Not really. No,
Is
this
it?
is no. It's really not. So basically, you're looking at n plus 1 and n, and that may be confusing you. So let's say backward time central space can also be written in this way. We're using, uh, sorry. So phi n I minus phi n minus 1 I. So this looks like a backward differencing, right?
Yes.
Then only difference is the other derivative, the one, the spatial derivative. That will look something like this in case of backward step. Does that make sense? So you're starting from n, going back at n plus 1, and the other derivatives also you're taking from n plus 1. Okay, no, sorry, I made a mistake here. So yeah, these will be n's. So this is also backward in time, central in space.
Because we are already taking all the unknown means current values.
Hmm.
Only
So
one phi I n minus 1 is taking from the
that's the
previous.
only known here. All the other ones are unknown.
Okay, so that's why it is backward and
Yeah,
that is forward. Okay,
yeah.
okay. Yeah, and one thing is like
Mm,
there is one method Jacobi where
mm,
we use all the previous values.
mm,
Then we go for Gauss-Seidel method where we have 2 point Gauss-Seidel and
mm,
line Gauss-Seidel. There
mm,
we use the current values,
mm.
right?
Yeah.
So uh, Jacobi is an explicit method, and Gauss-Seidels are implicit.
Point Gauss Seidel is not, but line Gauss Seidel is implicit. Yeah. Point Gauss Seidel
Okay,
only one
and
unknown is. Yeah.
yeah, and in which method, like even in Gauss-Seidel method, if we are
Mm.
using, we get tridiagonal matrix. Where do we get pentadiagonal matrix? In which
And
method we will get pentadiagonal?
yeah, so if you're using some 2D parabolic equations, so something like uh, this. If you discretize this, then you will get a pentadiagonal matrix.
Okay, but here in this course, like we like till now, what is discussed, we are only
Hmm.
getting tridiagonal.
Yeah, this can be simplified into two steps of two tridiagonal matrices. So that's what ADI is, alternating direction implicit. So where you do one X sweep, then one Y sweep, and ADI gives you tridiagonal matrices because we purposefully try to do that because tridiagonal matrices are easy to solve using Thomas algorithm. Okay, we have one question in the chat box. When
Okay,
will your next session take place? Next Tuesday again. Yeah, coming back to Shivang. So this is
okay,
what it is.
okay. But uh, like what I'm trying to say, like here we are not getting any pentadiagonal matrix. Like this same equation what you have used, if
Hmm.
we take only in x direction,
Yeah, if you're doing only
like we
X,
have to
only
take
Y,
we,
then no. But if you're doing both at once, then you will get a pentadiagonal matrix. So I think this was discussed in the lecture as well. Let's go back. We have the slides open, right? So I think it was the third lecture. Yeah, in 2D. So over here, okay, let's go to the implicit formulation. Yeah, over here we'll get a pentadiagonal matrix.
okay, and to solve this like do we need to we convert it into triangle by going
Yeah, we tweak the
row
method
by
a
row
little bit and do it, direction wise. We do X first, then Y. That's what the alternating direction implicit method is. And that gives us two different sets of tridiagonal matrices because those are easy to solve. We purposefully do that.
Okay. Yes. It's if you can quickly, if you
Hmm.
can explain that Thomas algorithm. Uh,
Thomas algorithm, okay. That was there in the lectures as well. I think this was discussed in the previous slide as well. So give me a second. If we look at week four slides, we had one
and this
question.
ADI is also is only useful for this pentadiagonals.
No, it can be used for 3D as well, where it will become heptadiagonal otherwise. So yeah, this is what TDMA is. Basically, you get a tridiagonal matrix like this. You can see my screen, right? Uh,
Yes.
sorry. So basically, we start with a tridiagonal matrix like this. We first of all eliminate the lower diagonal. That's the first step. Then in the second step, we go back from the bottom. So in the bottom, I have, one number. So this is the one. So if you look at you can follow my cursor, right? If I hover it over here, can you see it? So I have beta
Yeah.
n into xn equal to bn. So here beta and b are known. X is the only unknown. So I find out what xn is. Then I go to the above equation, the n minus 1th equation. Over there, I have xn minus 1 and xn. Xn used to be unknown, but now that I have solved the previous equation, I know what xn is. So that gives me xn plus 1. Then I keep going above and above in similar way. So in the next equation after this, I will have n minus 2 and n minus 1. So since I've already found out n minus 1 over here, that will help me find out what n minus 2 is. And that way I keep going back until I find out x2 and x1.
But in this, if you use ADI,
Hmm.
then like the,
No, ADI gives me a matrix which looks like this. Then I use this mathematics to solve for that.
okay, like the Thomas algorithm is used for all these Gauss Seidel and Jacobi as well. For
No,
Jacobi, we
no,
don't
no, no,
need
no,
that
no.
thing.
No, no,
For
no.
Gauss
For
Seidel,
Jacobi point Gauss Seidel, it's not needed. Only for line Gauss Seidel and these uh, parabolic implicit equations, then is when Thomas algorithm can be used.
can be used.
Yeah.
And for this, if we take this ADI thing
Hmm.
include in this thing,
Hmm.
then you have to repeat this process, like first going
Yeah.
row by row and then
Yeah.
going column by column. So
Yeah.
we need to update these values, like
Yeah.
first going row by row.
Hmm. Hmm.
So we make the same matrix,
Hmm.
calculate this p q and go up to n,
Hmm.
and then n minus 1 to calculate phi. Once phi
Yeah.
is ready, then we go by j in the y direction. In I mean to say
Hmm.
j
J
j
plus
index,
one.
right?
Yeah. 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 then again I, then
Yeah,
again J.
this
So
completes.
it keeps repeating. So if you try to look at a code of alternating direction implicit, so there will be one block of code which does an X sweep and another block which does a Y sweep.
Mm-hmm.
And it keeps going on in loop.
I see.
So we do X first, Y, then X, then Y, then X, then Y. That way.
Okay, okay. So it is only beneficial for line Gauss saddle and mean to say implicit schemes. Only for
Yeah,
those we have
yeah,
Thomas algorithm.
yeah, yeah.
Yeah,
Whenever we
because
get a,
anyway in the point and they're explicit.
hmm, yeah.
Yeah. Okay.
So it
And the
has to be
only way to
implicit
convert this
and
pentadiagonal.
what? Sorry.
Yeah, yeah. Please go ahead.
So it's only useful when it's explicit and when there are three unknowns in an equation. Then only you'll get a
Means tridiagonal. For
tridiagonal method.
pentadiagonal.
Yeah, we can't use that. Mm.
Okay. Okay. For because at one point it was told that we need to convert a pentadiagonal into tridiagonal to solve it.
No, no, we don't. We can't directly convert. We just discretize in a different way so that we get tridiagonal matrices. This way of discretizing in the ADI
Like that.
method is different from what we did over here, right? Yeah, over here.
No, the
Uh,
five
this,
point formula we get,
hmm,
the 5 point formula
hmm,
that give us pentadiagonal. Okay.
yeah.
In that, if we sweep x by, if we go row
Hmm,
by row and
hmm,
then
hmm,
by
hmm,
column, then we
hmm.
get tridiagonal,
Yeah, yeah. So,
or we get still we
which is
get.
what? So you're not using 5 point formula anymore. You're using 3 point formula now for those X sweeps
So
and
this
Y
is the way
sweeps.
to convert penta into.
Yeah. So
Is this
that's
the
what
way
I'm
to
telling. So
convert penta?
you're not directly converting penta to tridiagonal matrix, right? You're discretizing in a different way. So instead of a 5 point formula, you're using a 3 point formula now.
Okay,
You
okay,
get the point, right? So it's a different
and
method altogether.
okay, to some extent, and okay, yeah, and is about what are the condition for a matrix to be a sparse matrix? Like other than like if we say that
Yeah.
it has to be more number of zeros, like what number of
Yeah,
zeros?
so
Like
I don't
there
think
must be
there's
some
a,
criteria.
yeah, I get your question. I've even thought about this earlier. So there is no proper threshold, like, you know, let's say if 5% of all elements are uh, non-zero and rest are zero, then only we can call it sparse. There is no such five number or any specific number. So it really is a subjective thing, calling a matrix sparse or not.
Okay,
There is no objective
okay, and the
guideline that,
idea.
yeah.
Yeah, yeah, and the
Mm,
idea of this thing taking as approximate A as diagonal that comes from the formula itself. Like
mm,
we need to look into formula that
yeah,
I will look, and
yeah,
maybe then I will ask you again about that
sure.
if I don't. Yeah.
Yeah.
And only thing I don't, if you
Mm.
can again address that particular thing
Mm.
one more time,
Right.
I don't understand still the need of infinite for a pressure gradient to be zero, because my question, like the
Okay,
thing is
so
like
think about it this way.
that I understand.
Yeah, think about it this way. I'll tell you. So it's not the plate being infinite that is causing the pressure gradient to be zero. It's just that we don't need a pressure gradient over here. We even at the in the absence of the pressure gradient, we will get some flow due to the motion of the plate. That's what we are essentially trying to study.
Okay,
Okay, so it's not the plate being infinite that is causing pressure gradient to be zero. We're just holding pressure gradient zero and then seeing what happens to the flow.
okay,
Okay.
okay. And this thing where we don't need a pressure gradient to be zero,
Hmm.
uh, these are mostly near to the boundary, because otherwise shear effects will not be that effective. So such things are only possible in the proximity of this like boundaries. of plate or
Yeah.
anything, because
Yeah, and these are all idealized cases. These are not real life scenarios, right? So in real life scenarios, of course, due to motion,
always
some
we
pressure
need a
gradient.
pressure gradient.
Yeah, not always, but
Yeah.
it will be created due to motion, right?
Okay.
Yeah.
Okay.
Okay.
Thank you.
So cool. So now coming to my questions. So this is question number one of today's session, which is asking us what is the advantage of the implicit method over the explicit method for solving parabolic equations? Is it option A, that it is unconditionally stable? Option B, it can have a larger time step limit? Option C, it is more accurate? Or is it option D, that is both A and B? Okay, we have a response in favor of option A. Let's see what others have to say. Okay, we have another response in favor of option C. Let's take a look at the solution. It's actually D, that is both A and B. So all the sorry, all the implicit methods in general, they are unconditionally stable. So this is true. And being unconditionally stable allows you to have a larger time step limit without thinking about stability of your problem. So the correct answer should have been both A
But
and B. Yeah,
taking the larger step size will increase the truncation error.
it will increase, but you can still do it. Like you will still get convergent solutions. All
Yeah,
right.
but there is no such like, especially we have told the only limitation which is throws this method is that if we take a too much large steps time
Yeah,
step, then the truncation
uh,
error is.
this is compared to explicit methods. So it's not like we are taking huge time steps anyway, because otherwise we are not calculating the data that we may need. We will lose out on the information that we need. But we do not have that worry that we have in case of explicit methods, that even when you don't need a very fine time step data, you have to use a small time step just so that your method remains stable,
Yeah, okay, okay.
right?
Yeah, comparatively we can say that. Yeah.
Yeah. Okay, so moving on to the next question, it's asking us, question number two, that which of the following stability criteria is used for the explicit methods? Is it option A, CFL condition, or CFL criteria, you can call? Is it option B, von Neumann stability analysis? Is it option C, maximum principle? Or is it option D, none of the above? Okay, we have one response in favor of option B. So let's take a look at the solution. It's actually option A. It's von Neumann stability analysis is basically an analysis tool that gives us what the stability criteria is. And the stability criteria is often called the CFL condition or the CFL criteria. And CFL meaning the full form of it is Courant Frederick Lewis. These are the names of the three scientists who worked on this. And this criteria is what governs the limits of an explicit method. Okay. Moving on to the next question, question number three. Which of the following is not governed by a parabolic equation? So there are four examples here. So some of them are governed by parabolic equations, others are not. You have to, so most of them are governed by parabolic equations. One is not. You have to find out which one. So we have two responses, one in favor of option D, one in favor of option A. Let's take a look at, okay, either A or D. Okay, let's take a look at the solution. It's actually option D, steady heat diffusion, which is a elliptic problem. So basically, I have the Laplacian of T being equal to 0. The other problems, they are all parabolic equations. So unsteady heat diffusion, we saw earlier, it's dou T equal to alpha. And write this in Laplacians. Then boundary layer flow over flat plate, we saw earlier, these are governed by parabolic equations. So dou U dou X plus V dou U dou Y is equal to nu dou 2U dou Y squared. So this is a parabolic equation. Then Stokes' first problem is the problem that we were talking about earlier, an infinite plate which is sitting near a quiescent fluid, and this suddenly starts moving with a velocity u, and that sets up some velocity profile in the liquid above. Right. So once again, the governing equations of this problem is given by dou u dou t equal to nu dou 2u dou y squared. So this is what the Stokes first problem is. These are all parabolic equations. This is the only one that is elliptic in nature. So that's why option B should have been the correct answer. All right. So moving on to question number 4 now, which is a match the following type of question. So we have names of methods over here. Larson method, then Dufort-Frankel method, and Richardson method. And on the right hand side, we have the kinds of what kind those methods are. Are they explicit, implicit, or semi-implicit? You know, match the two columns with one another, and that should give you a combination which matches with one of the four options given below, which are A1, B2, C3, A3, B2, C1, A2, B3, C1, or A1, B3, C2. Okay, we have a very quick response in favor of option D. And another equally quick response in favor of option C. So let's take a look at the solution. It's actually option C that's correct. Good. So Larson method, as we saw, it's an implicit method, backward in time, central in space. Right? So this is BTCS, implicit method. Then Dufort-Frankel, will come to that later. So Richardson method first. So this is basically a CTCS method, and that gives us an explicit formulation. So C1. Now, but the problem is that this is unconditionally unstable. It never gives you correct solutions. So which is why Dufort-Frankel method got introduced, which is modified CTCS. So it takes the Richardson method and modifies it a little bit. So now this becomes an semi-implicit method. So that gives us A2, B3, and C1. Okay. Why semi? Because it's not exactly implicit, it's a modified implicit. That's why it's called semi-implicit. Okay. It is implicit, but with some modifications, not purely implicit. Larson method, the backward in time, central in space, that is pure implicit. Okay. All right. So moving on, we have another match the following type of way. What is pure? So without any modifications. Okay, so we have got another match the following type of question here. So once again, we have the same methods that we saw earlier.
Wait a minute. Wait a minute. Sorry, sorry.
Yeah.
It is difficult to write too much. Actually, the thing is, implicit is
Mm.
implicit. Like even if before modification, it is implicit. After modification, it is also implicit.
Yeah, but how do you
So
differentiate between the two?
no, my question is like we have not done any modification. It is implicit. After we have done modification, still it is implicit. So Sami means something like which is known. Like the word doesn't match.
Okay,
Sami.
I'll apologize for this. It's been a huge mistake on my part. Sorry. Let's move along to the next question. So we have another match the following type of question. So where we have the same methods that we saw earlier, Lasson and Dufort-Frankel and Richardson method, and the corresponding orders of those methods, the orders of the leading order errors of those methods. Once again, you have to match the method with the error that is there. Okay. Once again, we have very quick responses, one in favor of option B and one in favor of option D. So it's D that's correct. So basically, Lasonen method, it's a simple BTCS method. So that gives us first order in time, and since it's central in space, so it should be delta x square, that is second order in space. Then Richardson method is CTCS, right? So both in time you get uh, uh, second order accuracy as well as in space you get second order accuracy. So that's why C should be 2. And the Dufort-Frankel method, due to its weird nature, it has delta t square and delta x square because it starts out with a CTCS scheme. But due to the modifications introduced in it, the one additional error term comes, which is order of this delta t over delta x squared. So that's why the correct answer should be A1, B3, C2, which matches with option D. Okay. Any questions on this? So if not, let's keep rolling. We'll move on to question number 6 now. It is asking what is the which of the following is the order of accuracy of the Dufort-Frankel method? Now this should be easy. We just saw it. Okay. So we have one response in favor of option B. Okay, let's take a look at the solution. It's actually second order, so that's something that we saw in the previous slide as well. Okay, so moving on to sorry, question number 7 now. What is the stability criteria for alternating direction implicit for 3D parabolic equation? So basically, some equation like dou phi dou t equal to gamma. Then I have all three spatial derivatives here. So, okay, not t. So if I use ADI on this with x sweep, y sweep, z sweep, and okay, and these numbers, these gamma x, gamma y, gamma z, these are uh, units of diffusion coefficient. So these are like gamma delta t over delta x squared. Then this would be gamma delta t over delta y squared. and gamma z would be, sorry, yeah, and gamma z will be capital gamma delta t delta z squared. So what is the stability criteria for this? Is it that the sum of the gammas is equal to zero? Is it that the sum has to be less than half? Or is it that they have to be less than one thirds? Or is it that they have to be less than three halves? We have got one response telling that individual should be less than half. Overall, I don't know. Okay, let's see what others have to say. Okay, we have got another response in favor of option D, which is correct. So if you do perform the von Neumann stability analysis of a ADI method for 3D parabolic equations, this is what you get. So uh, it got the clue same that individually they should have been less than half. So as a sum, they should be less than three halves. It's not individual ones that set the criteria, it's the overall sum of them being less than three half, which ensures that the method will remain stable. Okay. So moving on to question number 8 now. So once again, I match the following type of question, and this should be easy because we just saw the ADI for 3D parabolic equations. So we have ADI for 2D equations and ADI for 3D equations on the left-hand column, and two conditions of stability on the right-hand column. So the first one being conditionally stable, and the second one being unconditionally stable. So what should it be? And over here, there can be repetitions. So as you can see in options C and D, it could be that both A and B correspond to 1, which is conditionally stable, or there could be option D, that is both are unconditionally stable. Okay, so D maybe. Okay, that was earlier. So C, D, not C. Okay, so we have one response in favor of option B and another one in favor of option A. Let's take a look at the solution. It's actually option B. So here's a funny little thing that happens. So in the earlier question, we saw that there was a stability criteria for ADI for 3D parabolic equations, right? So those were conditionally stable. However, in the 2D parabolic equation or even the 1D parabolic equation, if you do in an implicit way, those are all unconditionally stable, that for any case they are stable. So which is why it should be A2 and B1. So as we go from one dimension to two dimension, things are same. But as we move to the third dimension and do alternating direction implicit, then it stops being unconditionally stable and there's a condition of stability which arises. Okay. Any questions on this? If not, let's move along. We move on to question number 9 now. So this will require some calculations on your end. So the question is, what is the maximum time step that can be used to obtain a stable solution for a 1D unsteady heat conduction equation? So I'll write the equation for you. So dou dot T equal to alpha dou 2T to x squared using FTCS method for some given value of alpha and some given value of delta x. You have to find out what delta T is. Is it option A, 5 into 10 power minus 5 seconds? Is it option B, 5 into 10 power minus 6 seconds? Is it option C, 5 into 10 power minus 7 seconds? Or is it option D, 5 into 10 power minus 8 seconds? So the way to do this would be to go back to the stability criterion for this equation, which is gamma delta t over delta x squared has to be less than equal to half. So a little bit of algebra will tell you that delta t has to be less than gamma, uh, sorry, no, gamma over here. So delta x squared over 2 gamma. 10 into 10, 10 into 10 power 9. That's not within the options. I doubt it's correct. So let's do the math over here. So from here we get this, right? So delta x squared by 2 gamma. And gamma over here is nothing but alpha, which is the diffusion coefficient. Only 5 into 10 power minus 9 and C. 5 into 10 power minus 9 and another option that we got is C. Okay, so let's go through this calculation. So delta t has to be less than this. So the maximum value of delta t would be exactly equal to this. Would be equal to, then I'm just plugging in the numbers here. So delta x is 0.001 millimeters. So basically 10 power minus 6 meters squared. Then over here I have 2 and alpha is 1 into 10 power minus 6 meters squared per second. So I have 1 10 power minus 6. So 1 10 power minus 6, 1 10 power minus 6 I can cancel. Then I can say this is 10 into 10 power minus 7 by 2. Then this is 5. So ultimately it gives me 5 into 10 power minus 7 seconds, which is option C. So let's take a look at the solution. It is indeed option C. So this is the solution procedure for this sort of a problem. If you have any questions, you can ask. Okay, let's move along then to the last question of today's session, which is again a match the following type of question. So this is with respect to the beta method. So for different values of beta, what is it? Is it option A implicit, option B explicit, option C Crank-Nicolson? And the values of betas are beta equal to 0, beta equal to 1, and beta equal to zero point 0.5. Okay, we have a response in favor of option A. Okay, let's take a look at the solution. It's actually option D. So basically, what the Crank-Nicolson method does is, let's say if I have a parabolic equation, standard parabolic equation like this. So I'll break this down into one backward time central space and one um, forward time central space, and then uh, take a weighted sum of them with respect to beta. So basically, I'll write n plus 1 minus n by delta t. Over here, let's take gamma and delta x squared common outside. Then I'll have some beta into Pn plus 1, I plus 1, minus 2 Pi n plus 1, plus Pi minus 1 n plus 1. This is the implicit part, sort of. So at the n plus 1th time level. Then I have 1 minus beta into the explicit part, which is phi n I plus 1, then minus 2 phi n plus p I minus 1n. Yeah, that's what it is. So when beta equals 1, only this part remains. This part becomes 0. So then it becomes an implicit method. So A and 2 are related. And when beta equal to 0, it becomes a purely explicit method. So then it becomes beta equal to 0. And when I have beta exactly equal to half, that's what's known as the Crank-Nicholson method. So C should correspond to zero point 0.5, beta equal to zero point 0.5. All right, so there's another tidbit over here. So basically, as beta is between 0 and zero point 0.5, these are all conditionally stable. And as beta becomes equal to or greater than zero point 0.5, it becomes unconditionally stable, similar to what an implicit method would be. So it's the value of beta which determines the stability condition of these equations. So that's all. Thank you. Thanks for joining, and we will meet again next week.